Cool. Just make sure the whiteboard's lined up. Yeah. There we go. Cool.
Cool.
Thank
I
you.
love it.
Thank you. Because I might not be here. Dr. Yu,
Yes,
did you plan that lecture next Tuesday?
that is, she was asked.
Okay.
No lecture.
No lecture.
Lecture, the last lecture is next, Thursday.
Mhm.
And after that, the next Tuesday, I'll be here. If you have any question or you want to discuss some of problem, we can go through.
It'll be in this room or
I think this room, it'd be nice if people here, right? Student.
at the same time or?
That is also, I'm not sure if the other time this room is available or not. Maybe check with Missy. She is not yet together.
You guys want an apple?
Okay, मेरा शेव.
Just like in the mathematical one.
Okay.
Thank you very much.
Uncle, I have one.
Okay.
You have already
So, okay, since you all
I
asked
have
the
read it.
final exam,
Okay.
now let's make first, next is December is a Thursday, right? December 1st is the final exam and hope.
Yep.
That is this, and December 8th, that is Thursday, right?
Yep.
So that is the
We have some
final
programs.
exam in class. No, which time you prefer? That is next week, Thursday. Yeah. Yes, yeah.
The date of submission for the take home.
No, it's the same as yesterday. Yeah. So you will only have 1 week work on it. So in this day, let's first give me your preferred time and then I'm going to check with Missy. You prefer morning or afternoon?
Afternoon?
Afternoon.
Afternoon, which time is that? 1 or 2?
Which is
I'm
better?
probably available around 4 or 5 because I have to go to a program from 11:30 to 2.
Say again, from 11:30 to 2.
Yes.
So you prefer from 2, right?
I prefer from 4 or 5 p.m.
Oh, that's too late, right? 4 or 5 p.m. Then that usually 3 hours you have to go to like 7 or
So maybe-
finish.
Can we start from 3 to?
Can I start from?
Your program is 11:30 to 2.
Yes, I have.
And could you manage to come within hour?
Where is
1 hour or 3? From
Oh.
3 p.m.
3 p.m. Yeah.
Oh, 2 p.m. I
2 p.m. He
3,
cannot.
3 p.m.
She
3.
cannot.
3.
Yeah.
Maybe I can.
3 is fine?
Yeah.
Okay. All right. I don't know, right? Okay, so let's keep this one. I'm going to post on Blackboard. And of course, this is a turn on this day, right? So that you just will have one.
Yeah.
Okay, and all the open textbook, open notes, open your homework. You can put in the material you want. The cover chapter, right? So chapter 3, 8, 9, sorry, 9 and 10. I think today I'm going to discuss 10. I think 10 from chapter section 1. I guess maybe 3 or 4. Today we need two sections. 3, not 4. Let's go to. I'm not sure 4. That's this maybe 3. It's just definitely 3, right? So that is the cover. Okay. Now let's discuss the, I ignore this one since this is the angular momentum Poisson bracket because angular momentum is vector. So we discussed Poisson bracket or I assume this either components over the scalar, right? So how to deal with a vector, this is the topic. But that takes time. My class may not finish, so I just skip this one, and the exam will not cover this. So you just, if you're interested, you can read and let me know if you have any question. So today we are going to start here. Hopefully we can cover these 3 sections. So now, go back to the idea. Remember at the beginning of this class, our goal is try to solve the dynamic problem. In that, not the Newtonian mechanics, we go to the analytical mechanics. So we start from Lagrange. Remember, we start from Lagrange, which we introduce as the general coordinate and the general velocity. So what we need to do is solve this Lagrange equation. We all assume this force is, or the system is genomotic, right? So that the force can always write down in terms of the certain gradient of scalar potential. That is first, chapter 1. With chapter 1, chapter 2, chapter 3, always use this one, right? But what is one? This one is 2, we have a 2 second order, right? Partial differential. That is this. And we know the difficulty is because it's second order partial differential equation, we do not have a general solution. So it is really complicated, difficult to solve. Then we go to introduce Hamiltonian chapter 8. So we introduce Hamiltonian, right? And then we also convert the Hamiltonian, we introduce the kinetic variables, which is a function of general coordinates and the conjugate momentum. That is the topic. So that is the goal, try to reduce. And then with this Hamiltonian, we have this equation of Hamiltonian. Hamilton's equation of motion is, now we are going to do this time derivative of the general coordinate, that's the partial h, partial p, and the time derivative of this conjugate momentum is negative partial h, partial p. So here from 1 to n. Then here, this is the first order. Yes, we can reduce the order from second order to the first order partial differential equation, right? Okay. So we okay in general first order partial differential we can do usually, but it is difficult. It's difficult is a cross term in the equations. Sum of cross, that means it's QJ dot, the function is not purely QJ dot, but also with a PJ, and PJ dot also have some QJ. So that is difficult. Again, then we go to the idea, how to solve this. Even though it's first order partial derivative, a differential function, but still not easy. So the idea is if or the conjugate, we call this those p and j conjugate canonical variables, right? Are cyclic. Then right, so then we have this. Then this Pj dot partial h partial Pj is constant. So that is Qj dot. Qj is sum of constant, and Pj dot is minus partial h partial Qj equal to 0. That also gives us Pj is constant, right? And that makes things simple. Right, that is the idea. Now, how about in this case? Now the question is, how to realize, right? How to realize then? how to make this in general. In general, right? Those in general, they are not cyclic, right? And it definitely is not totally all, maybe a few of them, but not all, right? Are not all cyclic. So that means we have the idea about how to solve this. And thanks for the canonical transformation, chapter 9, right? So that's with the canonical transformation. We spend a lot of time to discuss the canonical transformation, the properties, how to transformation. So that means, yes, we can transfer the old canonical variables to the new one through the canonical transformation such that okay, Qj, Pj are all cyclic. It is possible, right? By this canonical transformation. So that is the method. That is the tool we are going to apply. So that is the strategy. And now, okay, that is, yes. Now we are going to see is how to make a canonical transformation such that, right? So that is, yes, we know the canonical transformation is possible, but then now our question, yes, okay, we agree, but how to do that? Which kind of, how to transform and remind this. Okay. Okay. That's it. Let's see this one. Okay. How to do that? So, if let's consider if this are cyclic, then what that means K must be a constant, right? Does not depend on this one. So suppose we have a canonical transformation such that both the new general coordinates and new conjugate momentum are cyclic, then the K does not depend, so that means sum of constant, right? Oh, I'll do this way. Okay, if K is constant, then, okay, that's this idea. So suppose we have a canonical transformation such that the new Hamiltonian is a constant. And it's constant definitely means these two are cyclic, right? So that is the, we can reach. So now the goal is how to make this one. And now, or more simple is just say 0. Constant, if I constantly subtract sum of constant is 0, right? So they are similar. If 0, then we definitely have capital Qj dot partial K partial capital Pj is equal to 0. Since K is 0, capital Pj dot equal to negative partial K partial capital Qj is also 0. So we have a Qj is constant and the Pj is constant. So now the goal is to make this equal to 0. How to find this canonical transformation such that the new Hamiltonian is 0. Can I erase this part? Let me make a picture so I can remember that. Oh, I didn't bring it, but I think I remember this. Just time is from 3, right? December is start on 3 p.m. Okay. Now the next job is how to make the canonical transformation, or how to find the generating function, right? We know the canonical transformations find the generating function such that we can convert from old canonical variable to the new one. So, okay. Okay, now remember the condition. If you remember in chapter 9, we discussed what is condition of canonical transformation is satisfy this, right? Pj Qj dot minus Hamiltonian is equal to this old one and the new one, capital Qj dot, capital Pj minus K plus the generating function, arbitrary generating function f, which is only function of, so that is condition, right? And we also discuss if the f equal to the type, right? The type I equal to 1, 2, 3, 4, which we discussed in chapter 9, is the type of f. So if this case, then we know this condition reduced to capital the new Hamiltonian is equal to the old Hamiltonian plus partial Fi partial T, right? This is an important equation we are going to start from here. Because our goal is to try to find the k equal to 0, then the k, if we find the generating function Fi type, then the k, the new Hamiltonian is old Hamiltonian plus this one. Okay. So now, right? So this is in general condition. Then, okay. So now our goal, right? So if we are going to find this new canonical, okay, let's do this. If we find this, there are either this canonical transformation or means a type of generating function such that k equal to 0. That means then we will have from here Hamiltonian Qj plus the partial Fi partial T equal to 0. Okay. This is all this is the idea is we call the Hamilton-Jacobi theory. Right up here, the Hamilton-Jacobi theory. Basically discussed it. Right? So up to here. And this one, this we can call this as a Hamilton-Jacobi equation. So now, you see the idea is, instead of solving the Hamilton equation of motion to solve the dynamics of system by solving this, we are going to solve this. And then you will see how the advantage of this. Okay, so now I'm going to erase this one, okay, right? Okay, so that once, since we already say that if k equal to 0, then we have this. That means we are going to find this by solving this equation. So now you see the goal. Okay, I just erased. The previous one we saw this Qj dot Pj dot by partial f h partial Pg or partial h partial Qj. Now we are going to find this because if this exists, And satisfy this equation, definitely after the canonical transformation is equal to 0, right? So that is, and that means this is we call it Hamilton-Jacob equation general. So if this is the case, right? In that case, we already, I think, that's enough. Okay. Then I'm going to discuss that. You could go to the details. All right. So up to here, then I say here, Fi, you can either select type 1, type 2, type 3, type 4, either. So now let's start from follow textbook, select the F2 type. But as I said, you can select any type. So that I want you to practice. So now, okay, now we are going to solve this equation. How to solve this equation? Example. Suppose, right? We select Fi is F2 type. So F2 type is the function of Qj and capital PJ, right? Because the generative function is always combined half of the old canonical variables and new half new canonical variables become as a bridge between old and new, right? This is here. So then the F2 type, if you remember in chapter 9 beginning, that is we use the old generative coordinates and the new conjugate momentum. That is F2. Okay. So if we select F2, now keep in mind this one. So now let's first go through this function. So now, what is the equation here in F2? Is Hamiltonian, which is function of Qj, old general coordinates, and the old general conjugate momentum T here, right? Plus partial F2, but F2 is Qj, capital PJ, T, partial T equal to 0, right? That is equation. And now, you see, if we solve this equation, because here we are going to, because these variables be Qj, PJ, capital PJ, since we are going to solve this one. So we need to replace the variable PJ in Hamiltonian, such that Hamiltonian is also function of Qj and capital PJ. Then you solve the equation, right? Solve this. So because if it's F2, and if you remember PJ, lower PJ is partial F2, partial Qj, right? And also capital Qj is partial F2, partial capital PJ. So we are going to substitute this into here. So this equation, same equation, but only change the variables. Hamiltonian, I'm going to just write in general, depending on system, the type of, so there's a general coordinate still here, but the conjugate momentum is partial F2, partial Qj, and T, and plus partial F2, Qj, capital PJ. Actually, this is details. So here, because F2 is Qj, capital PJ, T, right? And then T, and plus partial F2, Qj, capital PJ, T, partial T equal to 0. Okay, when we reach to here, now we are going to discuss. This is in F2 type of Jacobi, Hamilton-Jacobi equation. So if we select F2, we are going to solve this. We just replace this the variable in Hamiltonian by the conjugate momentum by this function of Qj and Pj. Now we discuss. Several issues we need to discuss. First, the number of variables. Okay. So here actually this is, now you see this is a function to solve this, right? Because this is unknown. We know Hamiltonian. Given system, we know Hamiltonian. But now, since we replace this PJ by the F2, and also we need solve this one. So actually, we are going to solve, give the solution for F2, right? So once we have F2, we'll come back to here, then our goal, what is goal? Finally, is find this, the dynamic PJ is PJT, right? That is our goal. We're going to find this dynamic, the all general coordinates, the function time, and the conjugate momentum. So that is how to describe the trajectory of the system, right, each particle. So that's scope. Then to read this scope, we need to find F2. How to find F2? And solve this equation. So now we discuss. Okay. So how many variables in this one? We do not know Qj, right? Qj, j from 1 to n, so we have n variables. We also have a t, right? So you see the variables in this the partial differential equation, this became a partial differential equation, or if you want to say that is partial differential equation for F2. Then you want to solve, so the number of variable is n plus 1, right? N is Qj. How many we have n Qj, and this one is t. If we do this integral, right, the number of integrals, if you do the solution, how many first order differential, the integral, you have the solution. So we have this. Okay. So if I have this and the solution, so we have n plus 1 integral, right? Integration. Okay, suppose we are going to use this as the integration of alpha g. G from 1 to n plus 1. That is the, assume that if we solve this one, we will find this actually, we will find this n plus 1, the integration. And then so we have the solution F2 is a function of Qj and alpha 1, alpha n plus 1, and t. Okay. So we call this, if it exists, this is a complete solution. This complete solution, now this is a constant. Since that are the integration, right? So that is finally, if it exists, if we solve this, our results be like this. And how much we'll have this constant. Okay, so now this is the first one. Second one, now we are going to denote, since you see here, I say either type, right? Fi, 1 type, 1, 2, 4, 5, 3, 4. So we select 1. So now we define the node S as a general is equal to, in this case, F2. I'm going to say general Fi. And in this case, if Fi equal to F2, so S equal to F2. That is a textbook here. So the F2 is Qj alpha 1, alpha n plus 1, right? So we define, that means the solution of Hamilton-Jacobi equation, that one we call this, we use this one S, so that is Hamilton's principal equation, function. Hamilton's principal function, which we are going to solve. Okay, so that is, so next time, if the question asks you, please find the principal function, Hamilton principal function, what does it mean? This. Okay, so give a name. All right, when this, so now this solution is not unique. because you see this is a partial differential equation, right? So the partial, you just solve this partial derivative, and partial derivative maybe add another constant or what. So the solution is not unique, but important information here, information which we can obtain from here, is that wherever exists generating function, now let's say either fi or now we use s such that we can have the new Hamiltonian equal to 0. That is important, right? Because that way we assume that's equal to 0. So we set equal to 0, then we are going to solve this equation by solving the generative function. So that means the solution, if it exists, that means it exists that the generative function. That particular generative function makes the canonical transformation, transform any Hamiltonian to the new one, which is 0. That is important, significant here. Okay. Furthermore, here, number 3, because s plus alpha is also the solution, right? Right, because since partial, okay, partial s plus alpha, partial qg is here, that equal to partial s, partial qg, right? So whether we add a constant, because when from here, when you solve this one, you have this m plus 1 constant, and one of them actually, when you do the integral, you have a constant, right? First order. So that constant, if it is really constant, then that's nothing, anything important, right? So or partial s plus alpha partial t is also partial s partial t, right? So what that means, the conclusion is we have m plus 1 constant. Actually, there's a 1 which is not important. It's additive for other solution. Because of this, right? Because it's so we drop the n plus 1's constant alpha n plus 1, which is additive, right? Which is additive term. Does not give us any importance. So now we will have F2 or S is the only function of is only n constant which are independent, which is alpha 1, alpha n, t. These are in the n constants, which are not additive, so are important to give us the significant or important physical information. Another one, which is not important, so we're going to do this. Okay, that is the second discussion. So now what we focus as the solution of associated with the integration, which is has n integrations. Now in number 4, now we are going to find a relation between, okay, why we ask this one? You see here, because F2, right, is a function of QG, capital PG, T, right? This is F2 type. The combination or mixture of half of the old general coordinates plus the half of the new conjugate momentum, and is also equal to either F2 or S, right? Q after the solution is alpha G t, right? This is the definition of F2. This is a solution of Hamilton-Jacob equation. So they are SB equivalent, right? So you see the relation between alpha j and pj. So after we got the solution, we have n integration constant alpha j thus we correspond to the new conjugate momentum, or you set equal, or function. So let me just in general we set equal. So here, if I do this, now I think you can also then come back to here. Since we know if k equal to 0, these are all cyclic, right? So that is constant. So definitely this consistent, right? Physically, also, if we know when we select after the canonical transformation, the new Hamilton is 0, so that all these new conjugate momentum are constant, are cyclic, then this be constant, and this constant has to correspond to each other. So here, that means there are several issues. Now I'm going to replace this. So because we know that, so the Hamilton-Jacobi equation here is rewrite, something rewrite at the beginning. To rewrite as this one. First, I just say this is capital PJ, but now Qj partial F2 partial Qj, but F2 is Qj alpha jt plus partial F2 Qj alpha jt partial t equal to 0. So at the beginning, you just immediately do that, because we know that's be constant. So now we do not know what is constant we are going to solve. However, we can replace the new conjugate moment as alpha when we solve this one. Then we are going to solve alpha, find alpha, right? So that is the information we have. That's the first one. Second one, then we know the old, if it's F2 type, right? So Pj is partial F2 partial Qj. Now F2 is Qj alpha jt. So definitely after you get this, the function of Qj alpha jt. Then capital Qj is partial F2 partial cap. Now I'm going to partial alpha j, since Pj is alpha j. See here. The psychological relation between capital Pj and alpha j. So here, this one, partial F2 is direct partial alpha Qj. And that be a function of Qj alpha jt. Okay. Now you will see we almost get this reach the goal. The goal is try to find this dynamics of the Qj as function time and Pj as function time. Old Qj and old Pj, right? So now if I say that is equation 1 equal to 2. So you can see here, this one, I have alpha j, I have t, but I have a Qj here, which we need to find the Pj, the transformation equation, or we need, our goal is try to Pj is function time, sorry, constant fine, but finally is, that is our goal, right? So we need to remove this one or replace this one. So let's do what happened. But here, at least we know the formula, but now we need to find this. Now, and the second one, this second one here, Qj, the Qj function of, okay, now I haven't finished. That's, molecules. Okay, so now Qj here, this one. This one should be because it is constant, right? Because K is 0. So both capital Qj and the capital Pj are cyclic coordinates, so the solution must be constant. So I'm going to use beta to distinguish the constant alpha j which correspond to this capital Pj. I'm going to use beta j correspond to capital Qj. So that means this is solution, but this solution should be function of Qj alpha jt, right? By to the partial, but the result is constant. So we have this, and then from here we can, since now you can see this, so this is only variable, so by inverse we can find Qj as function of alpha j beta j t, right? In principle. Okay, so now we have this. If I say this equation 3, then you are going to substitute equation 3 to equation 1. Then you have a Pj is Pj, which is a function Q, right? Q is a function of alpha j, beta j, t, and then alpha j and t. So that is Pj t. That is final result. So now you can see what we solve if we use the idea of Hamilton-Jacobi theory. We will not do this Hamilton's equation motion. We just solve the Hamilton-Jacobi equation, and the key is to try to find this F2 or the genetic function. Once we know the genetic function, we can find this canonical variables, for example, Qj and Pj, by using the relation since the F2 gives us the bridge between old and new, right? So that is the final the strategy. Here, actually the alpha j and beta j is correspond to the Q j when t equal to t naught, but the initial position or initial, they have this correspond. Later you will see, they do some example, you will see what is constant, and that makes sense since if this initial definitely is a constant, right? Initial condition, if this constant, and then we convert, make the canonical transformation such that those constant in the new canonical variable become variables, and because they are constant, so that means a cyclic, then that definitely have the Hamiltonian is 0. So, let's see. Okay. Now, before take some example, let's take some extension discussion. So here, with this relation, we can, since we have this relation, we can solve this, right? So I just almost give you this step. Okay, number 4 and 5. So in case, as I said, right, the solution, this is a solution. So that is all this, the integration which are constant from this to solve this one. So in general, we say they are one-to-one correspond. But sometimes, actually, the constant is not exactly one-to-one response. So maybe a function of another constant. So in general. Okay. The Pj is alpha j as a function gamma j. And these are integration. So suppose we have this integration or solution from this Hamilton-Jacobi equation, then this the new conjugate momentum. It is a function of the, but this constant is also constant. That's just a function of another constant. In this case, then we have Pj as partial. Okay, I use F2, right? So it's F2OS. P the OS, right? Partial Qj. That is, so that is function of Qj and alpha j, which is function of gamma j. So that is this case. And the capital Qj is partial F2, partial alpha j, not capital Qj, is equal to delta j. And that is, now, since alpha is a function of gamma, right? So this is a summation for all. It is I. Partial S, partial gamma I, partial gamma I, partial alpha j. If this case happens, of course, in the exam I will not let this happen, so not do this complicated. I just keep in mind, in general, this will happen. Now, number 6, we are going to see this significant or physical significance of S. Physical signification of this Hamilton's principal function S. In this case, F2, right? But you can also have F1 type, F3 type, F4 type. So now let's look at this one. Total time derivative for S. Example, S equal to F2 type. We just take the F2 type. So in this case, we know S is function of, okay, next step. So that is function of Qj. Let's say alpha j and t, right? So when we do the total time derivative, we need to the partial for each term. Summation of j partial s partial qj dot. Dot one, and then summation partial s partial alpha j dot, then partial s partial t, right? We have to do all the time derivative with respect to each individual variables. Now, what is this one? Partial s partial q. It's here, right? That is a pj. Pj dot, just right? I think sometimes I use f, but here actually that's equal to f2. It is s, right? It is equal to partial s partial q. This one is partial s partial q partial alpha. Since we select s equal to f2. So now, since here in this case, it is equal to this and plus what is term? Alpha j is constant, so it does not depend on time. So alpha j dot is 0, only this term. Now total time derivative for the Hamilton principal function is 2 terms. Now remember this term. Hamiltonian, right, is this term. Remember this? So because this, so the summation of Pj Qj dot is Hamiltonian plus Lagrange. Okay? I move the Lagrange to the left hand side. So now I can see here, now I keep continuing, so that is H plus L plus partial S plus partial T. That is the total time derivative of S. Now, who can tell me the next step? Equal to what? Remember this, I always use F2, okay. This equation is H plus partial S partial T equal to 0, right? So this equation, in general, we say S. And if S is F2, you just replace F2. Or, so this is a general, maybe at the beginning I use F2, Fi instead of this one. Now, since we introduced this Hamilton principal function, now the Hamilton-Jacobi equation is simply this one. That's equal to 0, because that's k, right? So now you can see here, this one plus this one 0, so that is equal to 0. Lagrangian. So the physical significance of this Hamilton's principal function is not by the total time derivative, is not by the Lagrangian. That is interesting. And people may say, okay, that's, since we are going to find this, therefore the S is just do the integral, total time with respect to time, t plus some constant, right? Then we can do that. Can we do? So if here, so we have the S can be do the integral directly, if we know the Lagrangian. Give a system, we know the Lagrangian. Then let's do the integral, then we can find this Hamilton's principal function origin, and then we come to here. So do that. Now the question is, keep in mind here. The Lagrangian is a function of Qj, because it's dependent on time, right? So that you have defined all the function of canonical variable as function of time, then you can do the integral of time. Otherwise, can you do that? We do not know Qj as function of time. We do not Pj as function of time. That is our goal, right? Here. We are going to find this. So if we do not know, it's impossible. Even though the relation is very clear, but it is impossible to obtain this Hamilton's principle. So we have to go back to solve this Hamilton-Jacobi equation. That is discussion number 6. Now we have more discussion, almost, and then we can take the examples. Number 7. Okay, in case if the Hamiltonian does not depend on time explicitly, you will see this equation is reduced to some others. Okay. If this is right, so since the Hamiltonian plus partial s partial t equal to 0, so if we do the partial derivative on both sides, it's still equal to 0, right? Well, that means because this is 0, so we have a second order partial derivative of this Hamilton's principal function, 0. If that 0 means the first order partial derivative is some constant, right? And here I'm going to introduce this constant minus alpha 1. Textbook use alpha, I think I would like to use alpha 1 because that is one of the parameter alpha g. So let's give it the order. So that is defined. Defined as a negative. Why did use negative? Any constant, but I define this constant as negative alpha 1. So what happened? Okay, in that case, then let's go back to the Hamilton-Jacobi equation. H plus partial s partial t equal to h minus alpha 1, right? Because partial s partial t is negative alpha 1 equal to 0 in this case. So the Jacobi equation becomes more clear here. So Hamiltonian is equal to alpha 1, which is constant. This constant, or constant, right? So that is the over new constant you are going to solve. So Hamiltonian may be a function of Qj, Pj, and because that's not depend on time. So that equal to this alpha 1. This one is energy, is this one. So we got this, we really got this from this Jacobi, Hamilton-Jacobi equation. That is important. And once we have this, so now you can see here, the first order partial derivative, this one, then we can also have the Hamilton's principal function s is which is function Qj alpha Gt, right? And now it is here. since we have one term, so the minus alpha 1, you just do the integral, right? Do the partial and you do the integrals, you get the s. The first integral is t, right? This time t. Some constant, right? This constant, since this is a constant, we include qj and alpha j. But still, that does not depend on time explicitly, right? So now this is about the height. So then, that is from here, you can, okay, I just use this one. So, that is, this partial s is minus alpha 1 t, right? Plus constant qj alpha j, and then here is minus alpha 1t plus constant. This constant is again another function of qj and alpha j. Then we are going to define this one as w, capital W. qj alpha j, and the name of this one is Hamilton's characteristic function. This function does not depend on time explicitly, but implicitly, since the qj is a function. So now we see the s here, right? So s is equal to this. That means we have time derivative explicitly depend on time, only this term, linear. And then plus another term, which is a characterized function, does not depend on time explicitly. So if this is s we have, then you can see here, you can go to then so now the Pj is partial s, partial qj, right? Now s here. So that is, this term does not depend on qj, right? But we just have it. This is partial minus alpha 1 t plus w qj alpha j partial qj. And that is only depend on partial, the characterized function only, since that partial derivative is only for respect to qj, not time, right? qj alpha j partial qj, which is function of qj. If, this is the condition, if Hamiltonian does not depend on time explicitly, and this is a more popular case, very general, right? So then next one, the capital qj is partial s partial alpha j, right? Okay, so here is partial minus alpha 1 t plus characterized function qj alpha j partial alpha j. Then this dependent, j equal to 1 and j equal to others is different, right? So if a j equal to 1, is this one is a minus t. If the partial alpha 1 minus t plus partial w partial alpha 1, so j equal to 1 case, right? The others, this disappeared, only this one. So the others partial w partial alpha j not equal to 1. And of course, not equal to beta j. It must be constant. So beta 1 should be this one, beta others should be this one, right? Okay. This almost finished. Now I'm give a brief summary. of the Hamilton-Jacobi series or equation. So we start from this Hamilton from here, right? If we solve the equation of Hamiltonian, we need to solve this. G, which reduce to. From here, we're going to find Qg as a function of Qgp and Pg as a function of Pg. That is Hamilton's equation motion. But then from here, we go to this the Hamilton-Jacobi equation or theory that is reduced to k equal to h plus partial fi partial t equal to 0. So by this, we can find this capital Qj dot is constant. Okay, 0. So the Qj dot, Qj is, I'm going to give beta j and capital Pj dot. So capital Pj is alpha j, right? That is different. So here, this is after the canonical transformation. We come to here. Initial solve this and the canonical transformation, so that is this is a Hamilton's equation, right? Okay, and from here, what we need to do is, okay, so now the key is this one, right? So now I'm going to describe generally. If fi equal to s equal to f2 type, then we have this relation Pj is partial s partial Qj and the capital Qj is partial s partial alpha j. Okay, and what you are going to solve is, in this case, this equation becomes Hamiltonian is Qj partial s partial Qj, since Pj is partial s here, and t plus partial s partial t, which is Qj alpha j t equal to 0. We are going to solve this. And from here, the remaining part we know. So that is case if this is F2. This is so far we discussed. Now I give you some idea about others. If Fi is the Hamilton's principal function, which is F1 type. F1 is this one, right? Okay, so what is the Hamilton-Jacobi equation in this case? Okay. So in this case, we know Pj is partial s partial Qj, and capital Pj is negative partial s partial. Then your Hamiltonian, the Hamilton-Jacobi equation is here. Now, Qj is still here. Pj is partial s partial Qj, and here t plus partial s partial t, which s is function Qj. Now, I can use here is okay. This is this one. So I'm going to use. Let me just use capital Qj. But this is a beta j, right? You're going to solve this. this one is beta G. So the remaining part you solve this, when you solve this, find this, and you come to here. So it must be P G function Q G beta G T. And that is alpha. Which is alpha G is a function of Q G beta G T. That is in case, so now just this space. If F3 if Fi is F3 type, F3 type is PJ, QJ, right? Then here, since we know F3 is QJ, is negative partial S, partial PJ, and the capital PJ is negative partial S, partial capital PJ, or minus partial S, partial beta T, right? So the Hamilton-Jacobi equation is written here. Is now we are going to replace QJ since it's a function PJ and capital QJ. So Hamilton QJ is used to minus partial S, partial PJ. Here is this one, come here. Then PJ, P plus partial S, which is function of PJ, QJ, which is beta J, T, partial T equal to 0. So you are going to solve this one. Here, the variable is PJ and capital QJ. Capital QJ is a function, is a constant. Okay. Now, if we select F4 type, which is lower PJ and capital PJ, or this one, or this one is alpha G, right? So, because in the F4 type, QJ is negative partial S, partial PJ. Capital QJ is partial S, partial capital PJ is partial S, partial alpha G. So, the Hamilton-Jacobi equation became Hamiltonian. Again, we are replace QJ by negative partial S, partial PJ, and PJ, P, plus partial S, which is a function of PJ, alpha J, T, equal to 0. So, see here, depend on which type you're going to select. Then you have this different type. Let's see how much you can do. Now we are going to take examples, see how we apply the Hamilton-Jacobi equation to solve this dynamics and find solution. Example. One dimension simple harmonic equation. Let's do this. First, one dimension, so the variable is only one, right? One is Q, another P. Okay, so now let's first Hamiltonian. Hamiltonian, one dimension simple harmonic, we have the kinetic energy. Kinetic energy, okay, let me first the first one, kinetic energy, right? Plus potential fluctuation, so we have half of m omega squared Q squared. that is, of course, in this case, we select, if one dimension, we select Q is just X, right? P just PX. That is first, that is already chapter 8 or chapter 1, 2 is first learn how to select general coordinates and conjugate momentum. So we already jumped that, so we come to here immediately. So once we have this, okay, now I'm going to by the products, yeah, let me ask you, is equal to energy? Remember, if the Hamiltonian equal to energy, what's the condition? First, partial Ri, partial T equal to 0, right? Second, the total kinetic is a projector. And of course, the potential V is only function of general coordinates. So if this satisfies, and here you see this projector, this also is a function Q, right? The kinetic energy is only projector, yes, and the potential is only function of general coordinates. And the general code does not depend on time explicitly. So yes. First, so just remind you, we learned this before. Okay, so now this is the first judge. Now we are going to define which type we are going to select. F1 type, F2 type, F3 type, F4 type. So let's select. Now this is a okay. That's step 1. Define or select Fi is F2 type, which is S, which is a function of Q here, and alpha, if I use alpha. Here should be J, but since we have only one dimension, I can remove J, right? J equal to 1. J equal to, or J equal to 1 to n, but n equal to 1, right, in this case. Just give you the idea why I remove this index J. Because here, we only have one dimension, so J is 1. So here, I only use Q alpha. Okay. That is the first thing. So once we define this function, then we have, immediately we have P is partial S, partial Q, right? F2 type, remember? Partial S, partial Q. Okay, so that is one. Okay, then the capital Q is partial S, partial alpha P, right? So that means once we select F2 type, the Hamilton's principal functions be like this, and then they correspond to the old canonical conjugate of momentum is this one, and the new general coordinates be this one. So that is we first define. That is your first step to define. Then once we have defined this type of this geometric function, then we can go to step 2, is apply Hamilton-Jacob equation. Okay, here Hamiltonian is Q, P, T, let me write out in general, plus partial S, Q, alpha, T, partial T equal to 0. Because here, right, P is partial S, partial Q. So this one is we write the Hamiltonian Q partial S, partial Q, T plus partial S, Q alpha T, partial T equal to 0, right? Okay. That is step 2, we'll write down here. Now we can do further analysis. When we discuss, there's one point, so step 3. Let's look this one. Hamiltonian does not depend on time explicitly, right? So we immediately know there are several issues. Hamiltonian is equal to alpha. Okay, now let's do this way. This first one is S, positive S, positive T is minus alpha, right? So that gives us okay, that is the first one. Second one is S, and it is also equal to energy since we analyze here, right? Hamiltonian is energy, so now the immediate value is if we know alpha, we know energy. Second one is the Hamilton's principal function is minus alpha t plus the characteristic function w, which is only function q and alpha, right? So that is the immediate we got is the second. Okay, let me stop here, and I think we have time. On Thursday, I'm going to play at least maybe one or two examples. See how much time we can. I think that's probably enough, and we can play this, and that also help you to how to solve this Hamilton-Jacobi equation and solve this the dynamic problem. That is our goal. This whole class. At the beginning, we introduced Lagrange, then we introduced Hamiltonian. Now we have this Hamiltonian. Hamilton's principal function, or Hamilton-Jacobi equation, which apply the canonical transformation, so we reach the general formula or general way to solve this the problem. All right, so Thursday I'm going to deliver this final exam take at home. Then you can start to do that. And next Thursday, we will have this final class, examining class.
Sounds good.
Yeah, okay, yeah, just think it's about, okay.
Oh, this Thursday, we have a test in mathematical physics.
Oh, okay.
So you probably can't get it.
So, yeah, then I can maybe finish a little early, so then next Tuesday we can keep continuing this kind of discuss. So next Tuesday, which time still the class time? Let's first the class, you will have no any class, right? Let's first fix the class time, and then I'm going, if morning you have something to do?
Nothing in one.
Nothing. How about you?
I'm good.
Okay, I'm going to check this message. If a morning is okay, let's start at like 10, so we can discuss in an hour. If you have any question, since that time you already have a home, the exam take at home, right? Okay, good, good.
Thank you.
Okay.
Hey, what's up? How's it going?
Pretty good. I guess. How do you quantify that?
Oh, discreetly? Not
Hi,
it's like a broad spectrum. Intangible happiness.
How about this interview? You are so fast, or just stay here? So you have another.
Sigma.
You have a-
Define happiness, yeah, no, we have to,
Thesis.
6 months, okay.
let's see,
Okay.
the delta's here.
the challenge. Thank you. You will come. Take care.
Minus epsilon. This is delta plus epsilon. So, happiness is like,
Yeah.
it's between this.
You gotta count for the error.
Hey.
Other classes. Hi, how are you?
Chandra. We are now replacing the battery. So, there's only one new step. Stop recording. Press the record button.